We present batch exploration with examples for scalable robotic reinforcement learning. We're inspired by the goal of a general-purpose robotic agent, which is capable of generalizing to new tasks, environments, and objects. In the fields of computer vision and NLP, recent progress has shown that large and diverse datasets combined with expressive models are a path towards such generalization. To that end, we are interested in the question of how can we collect large and diverse datasets for robotic manipulation? A number of challenges make robotic data collection hard. First, robotic data collection requires a physical robot interacting in an environment. But to be useful, this interaction needs to consist of meaningful behaviors. While humans can help provide such meaningful data, using them in the loop of data collection makes data collection difficult to do at scale. On one end of the spectrum, completely random exploration can be run at a very large scale, completely unsupervised. But the data it collects is generally of a lower quality. On the other hand, human demonstrations can collect far more meaningful interactions, but are difficult to do at scale due to their dependence on a human in the loop. We ask the question, can we collect high-quality data without depending on a human in the loop? A natural choice to address this problem is to employ unsupervised novelty-seeking methods, which use an intrinsic reward to try and capture more meaningful behavior. However, we found that deploying such a method in a vision-based manipulation setting performed poorly. One challenge for such methods is that they have to explore everything in large high-dimensional state spaces, but in reality, only some subset of interactions are actually useful. Our key insight is that we can leverage some weak human supervision before data collection to guide exploration. Such an approach is beneficial because the agent can learn to explore meaningful interactions guided by the human data, while not needing human supervision in the loop, so the entire data collection process can be run unsupervised and at scale. Concretely, we propose batch exploration with examples, or B. In the B framework, a human first provides some weak human supervision on what states are relevant to explore, in our case by providing a modest number of example relevant states. The agent then collects useful data guided by the supervision without needing the human in the loop. Then any offline RL approaches can be applied to the collected data, either by using goal condition methods or by augmenting the collected data with reward labels offline. Lastly, the learned policies can be applied to any downstream tasks for which the collected data was relevant.
So how exactly does B work? B learns two models. First, it learns an ensemble of discriminators which differentiate between the human-provided relevant states and the agent's own experience. These discriminators provide a metric for how relevant a new state is. Second, B learns a latent dynamics model, which it uses to plan its exploratory actions. To choose actions, B aims to explore around states it estimates are relevant or has high uncertainty in. Concretely, B performs model predictive control using the latent dynamics model, where the reward function is a max score over the ensemble of discriminators, guiding the agent towards states with high relevance or uncertainty. In our experiments, we test B on several simulated manipulation domains involving blocks, a door, and a drawer. We also test on a real Franca robot interacting with a desk. We compare B to a state-of-the-art task-agnostic exploration strategy using model disagreement, as well as state marginal matching, another exploration technique which utilizes the human-provided weak supervision. Lastly, we also compare it to random exploration. We observed that across 6 simulated settings, B interacts with the relevant object more than twice as often as the comparisons. Furthermore, we find that B can be used to explore multiple objects simultaneously. Next, we find that when using the collected data for downstream planning for goal-reaching tasks, B improves performance on 4 out of 5 tasks. Lastly, we study if B is effective in a real robot setting where we wanted to interact with a small drawer on a desk. We're able to collect weak human supervision in a matter of minutes. With this supervision, B is able to effectively explore the drawer and collect high-quality data autonomously for a day or two. B interacts with the drawer an order of magnitude more than disagreement and yields a 20% higher success rate in the downstream task of closing an open drawer.